Welcome to section 7.5 in what might be the shortest video this year. Let's see. So the reason for this being a brief section is that we're not looking at any new methods for solving linear systems. We're just looking at a couple of special types of linear systems. Now so far we've worked with consistent independent linear systems. Consistent meaning that when we had two equations there was at least one point that would satisfy both equations. Independent means that we don't have the same equation twice, and that provides us with only one solution rather than more than one. So consistent independent linear systems have exactly one solution, but sometimes we could run into another type of system. So for example, we could see an inconsistent system, and this is where we have no solution. So there's no one single point that will be on both lines or will satisfy both equations in our system. We could also have a consistent dependent system, and that's a linear system with infinitely many solutions. Now let's see how that works and why that turns out to be that way. So notice in our example the directions say solve each system, and the directions do not specify using graphing or substitution or elimination. We get to choose. Now notice in the first case we already have y equals, so having y by itself, this is set up very nicely for substitution. So we can take that expression 3x minus 14 and substitute in place of y in the first equation. That's going to give us 6x minus 2 times 3x minus 14 is equal to 28. Then we can apply the distributive property. We get 6x, and then negative 2 times 3x will give us negative 6x. Negative 2 times negative 14 plus 28 is equal to 28. And then 6x minus 6x is 0. Those x's just drop right out, and we have 28 equals 28. So when you have two equations and you perform a substitution or an elimination step and you end up with a number equal to itself, this is a case where we have infinitely many solutions. And let's take a look at why that is true. Notice that the second equation is already in slope-intercept form. We know we have a y-intercept of negative 14 and a slope of 3. Well, what if you take that first equation and rearrange it in slope-intercept form? So if we subtract 6x from each side, we get negative 2y equals negative 6x plus 28, and then divide by negative 2, and we get y equals a positive 3x and then minus 14, which is the same as our second equation. So if you were to plot this, and let's say you plotted the first one because it's already in slope-intercept form, you would have a y-intercept of negative 14, a slope of 3, so something like this, and you draw your line, and then you go to draw the second, or rather the first equation, and maybe in this case you use the x and y intercepts, you're going to end up with the same line. And what that means is every point that's on that line satisfies both equations because these are equivalent equations. Okay, now notice we didn't say all real numbers here because we're in two dimensions. And so any point over here will not work, any point over here will not work, but any point that's on the line will work, and because there are an infinite number of points on a line, there are infinitely many solutions. Let's look at a different scenario in number 2, where we have 5x minus 7y, negative 5x plus 7y. Notice this is set up very nicely for elimination. So if you look at the x terms, we have 5x and negative 5x, opposite signs, so we go ahead and add those. 5x plus negative 5x is 0, so we've eliminated x. But then when we look at the y's, negative 7y plus 7y is also 0. So we've also eliminated y here, so we end up with 0. And then negative 30 plus 28 is negative 2. But 0 will of course never equal negative 2, and that tells us there's no solution. So then, if you wanted to see why that is, let's look at that first equation and rewrite it in slope-intercept form. So if we subtract 5x from each side, it becomes a negative 5x on the other side. And then divide by negative 7, we get y equals a positive 5 over 7x plus 30 over 7. Now look at our second equation where we have negative 5x plus 7y is equal to 28. So now we're going to add 5x to each side. So we get 5x plus 28. And then divide by 7, we get that same slope of 5/7, but now we get a different y-intercept of 4. So 5/7, 5/7, parallel lines, but different y-intercepts. The two lines will never intersect, and that's why there's no solution. Okay, so these are the two cases to look out for: infinitely many solutions or no solution. Good luck, enjoy, and I bet you wish all sections were this brief.